Okay, so this is Math 7, Chapter 7, Section 3, Products, Quotients, and Roots of Monomials. We're going to continue to use what we've learned about exponents, multiplying them, dividing them, raising them to powers, but we're going to use more complex terms now, okay? So we have to define monomial, and we just said it means a single term. So a term can be many things, so we're going to put a number of examples down here. It could be just a number. So here's an example, 7. 7 is a single term by itself. It could be combined with other terms, as long as they're like terms. What term could be combined with 7? 7 plus 8. Okay, 7 plus 8. We can combine it, as long as it's a like term, we can combine it, right? What is 7 plus 8? 15, good. So that's another term. That's another monomial, 15 by itself. Okay? It could also be just a variable. So there's x. X is a plain old variable by itself. What is the invisible number, the coefficient in front of the x, everyone?
1.
Good, 1. I have 1x. So can somebody give us another term that could be combined with 1x? 1x plus, Emily? 2x. What is 1x plus 2x? 3x. Good. As long as they're like terms, you could combine them. 3x is another monomial because it is a product of a number and a variable. 7x is like 3x, right? 7x. Look at that. It's a product, but it's considered a single term because you could add it to another term. So somebody give me another term we could add to 7x. Chris. Okay, just the one we just said, 3x. 7x plus 3x is 10x. Okay, so they're like terms. They have the same variable attached to them, okay? We can even get fancier. We can have 7x to the 4th. There's our exponents coming in. This term, 7x to the 4th, is a monomial. It's a single term. It could be added to other terms as long as it is added to a like term, right? So who can give us something like this that could be combined with 7x to the 4th? Riley?
4x.
7x to the 4th and 4x. Are those like terms? 7x to the 4th, she says, and 4x. Can we combine those? Why can we not combine those? Dylan?
Does it have to have an exponent?
Would have to have, okay, but it does have an exponent. What is the exponent for this x here? It's 1. When you don't see an exponent, there is an invisible 1. I have one factor of x. So these are not like terms because the x's would have to have what? Hannah? The same exponent. Okay, so these are not, if it said 4 here, now they have the same exponent. And we could say we can add them. What is 7x to the 4th plus 4x to the 4th? Say it louder. 11x to the 4th. But when it had just a 1, or that invisible 1, right, they're not like terms. Okay, we'll come back to that example later. But this is not a monomial. These are 2. Oops. Okay, another monomial might be even more complicated. It might be this, 7x to the 4th, y to the 3rd. 7x to the 4th, y to the 3rd has 3 different kinds of factors. Can anybody give me a term we could add to this one? Rachel?
2x to the 4th, y to the 3rd.
Very good. So do you hear how her variables have the same exponents as this? So what would this 7x to the 4th, y to the 3rd, plus 2x to the 4th, y to the 3rd equal?
9x to the 4th,
Y to the 3rd, good. So 9 of them, right. And finally, we could have a negative term. That's also a monomial. Negative 7x, I could combine with another term up here. Which other term or terms could I combine that one with? Chris? Good. What is 7x plus negative 7x? Say it louder. 0. They're opposites. 7x, it's like I have 7 puppies, take away 7 puppies. I have no puppies, 0. Okay. Okay, these are monomials, one single terms, right? These are not monomials, what you're about to see. And here's one here. Anyway, let's start with this one here. This is not a monomial. It says 7 plus x. How many terms are there in this expression? 2 terms. So rather than a monomial, we call it a binomial. Bi means 2. Bi, can you say that? Binomial. Good, it means 2. So 7 plus x. Can we combine 7 plus x? 7 plus x equals? 7 plus x equals 7 plus x. 7 plus x does not equal 7 times x. It doesn't equal 7x. 7x would be times, right? That's different than addition. Okay, so they're not like terms, they're separate, 2 terms. Okay, here's another example. 7x minus y. Can you combine 7x and a negative y? No. So we leave them separate. It's called a binomial. And then the one that was not covered here, 7x squared plus 3x plus 2, that is called, it's, how many terms does it have? 3. So instead of a binomial, it's a trinomial. Very good. Okay, and can we combine any of these terms in the trinomial? No, they're just like unlike terms. They don't have the same thing. Okay, so it reminds me of this one up here, which had unlike terms. So here's a way to look at this. It's as though I have 7 iPads, 7x to the 4th. Let's say x to the 4th are iPads. And x's, I have 4 of them, but they're not iPads. They are iTouches. So they have something in common, right? They both are made by Apple. But these are iPads, these are iTouches. If I have 7 iPads plus 4 iTouches, do I have 11 of anything? No. They are separate. They're kind of alike. They're both x's, but they're not the same thing. Okay? So they must have the same variables to the same degree, the same exponent, in order to be combined. Okay? So we're going to work with these now. We're going to start by finding the products of them. Okay? So go ahead and pause and make sure you take down these examples. Okay, what we're going to do is find the product of these monomials. We can only add like terms, but you can multiply unlike terms all the time. Can we multiply x times y? We call it xy. It's unlike. That's fine. Okay? So we do that all the time, and we're going to do that here. What I want to do is expand these as we go, like we did yesterday, so you have a good feel for this. So who can expand this and tell us what all the separate little factors are here? Do I have a volunteer? Nick? 7 times b
times 3 times b times b.
Excellent. Okay, so he took b squared and he said it is b times b. Everything is pulled apart like a slinky. We've expanded it. Okay, so now we can try to multiply together the like things. What allows us to multiply 7 times 3? What property of multiplication allows us to do that first? Chris? We need a property that allows us to move the 3 near the 7. Commutative, excellent. Okay, what is 7 times 3? 21. And then we have times b, and how many factors of b are there?
3.
1, 2, 3. Good, so we can say b to the 3rd. So there it is. Okay, so 7b times 3b squared is 21b to the 3rd when you bring it all back together. Okay, go ahead and try that again. Expand this. So let me hear from somebody else. How about Courtney? Can you expand this?
Yes. 3 times c times another c times b
Excellent. Okay, so we're going to start by multiplying our numbers. 3 times 9 is
27.
good. And then we're going to put the variable factors in alphabetical order. Okay, so C comes first. How many C's do we have? 3, 4, 5. C to the 5th. And then how many D's, Courtney?
2.
1, 2. D squared. And there you go. You have it. Excellent. So we're going from here to here, ultimately. 3 times 9 is 27. I have 5 C's and I have 2 D's. And there we go. Okay? This one we can expand a little differently because we have this big term, 4x to the 5th, y to the 6th, happening how many times? 4 times. So good. So we can do what, Ryan? How can we write that?
4x to the 5th, y to the 6th, repeat. And then do it again. And then do it one more time.
There you go. Good. So really expanded. You're showing this big term is a factor 4 times. So how many factors of 4 do we have? Ryan?
4,
So we could write that as 4 to the
4,
4th. And how many factors of x do we have? How many do we have just right here? 5, and then
10,
10,
15,
15,
20,
20. So we have x to the,
20,
good. And then we have y's, right? How many here?
6,
6,
12,
12,
18,
18,
24.
24 to the 24th. Now we could expand out all of these x's and y's, but that would take up a lot of space. Do we have any questions so far? Does everyone see how this works? Now the 4 to the 4th we could evaluate. So this current answer is fine using exponents, but what is 4 to the 4th? 4 times 4 is, and so we end up with 16 times 16, really. 16 times 16, 16 squared is 256. It's on the wall in the classroom. The first 20 squares are on the wall there of the classroom. So try to get familiar with those. Okay, so we're going to try these and then come back and check your answer when you have tried them. Okay, so try them out. This number 3 is the tougher one, so we're going to do this for the video. If you're on the video, you can pause it and check 1 and 2 yourself. But here we go, Rachel. What is it?
4 times C times D times D times D times negative C.
Okay, so this, what is the number in front of the c squared?
1.
1. So it's really a negative what?
1
Negative 1 times c
times C
times c. The negative is not being squared. Good.
times
Times
D.
d. So we have a negative 1 that was a little bit invisible there, but now you made it visible. Good. So now what?
And then 4 times negative 1
Is
negative 4. And C to the 3rd powers
c to the 3rd.
and D to the 4th.
Awesome job. Way to go. Way to go. Okay, so make sure you pause the video and check out the answers to number 1, 2, and 4 as well. And then you're ready to move on. And so now we're going to just do 3 problems that involve quotients. Okay? Okay, the strategy that we could take is expanding it again. So we know that if we have 12b to the 6th, that's what is the operation between the 12 and the b to the 6th? This operation up here is multiplication. So, and the same with the denominator. So we could pull the 2 pieces apart that are like terms and expand it this way. Because multiplication of fractions is just multiply across the top, multiply across the bottom. So now we're just going to divide the like terms, right? So what is 12 divided by 4? And b to the 6th over b to the 2nd. There's 6 b's on top and 2 on the bottom, so we have b to the 4th. Good job.